Alright guys, so welcome back. Hope you guys had a nice restful break. You got a good feel for how the class works last semester. Maybe you found some kinks in how things were going for you, and now you kind of have a chance to kind of start fresh with your grade, right? And know how to get where you need to be, okay? So we're going to be doing a couple units first, and then we'll actually be hitting up some trigonometry later on this year. So let's go ahead and jump in and get started. This one's going to be about exponential functions. You guys should be able to tell me what an exponential function is. You should be able to identify what the equation of an exponential function looks like. And you should be able to tell me the parts of the equation and what they represent. Okay. Oh, and we're also going to talk about calculators. Sometimes that's a little bit hard. People know how to use the calculators with exponential and logarithmic functions, so we're going to be practicing that a little bit today. So let's begin. Take a look at guided practice. Read that over really quick. It says Esteban went to school sick. After a day went by, he got 2 people sick, and then those people got 2 people sick, and by the second day, and so on. So that every day the number of people infected by the sickness doubled. So we're going to complete the table. So on day 0, there's only 1 person sick. It's Esteban. On day 2, on the first day after that, though, right, after 1 day's gone by, 2 people got sick. On the second day, after the second day's gone by, how many people will be sick? 4. How about on the third day? It's going to be 8. Now here's why. Because every day is doubling, right? And so if these 4 people all got 2 people sick, right, that's going to be 8 people. All right, so why don't you guys, let's see, what do you guys think about this one? What's the next one going to be? 16? And then the last one? Good catch. That's a tricky one. I almost said 32 also, but look at the number there. What's that say? Well, I'll show you how we can get that number quickly in just a second, but good job. See how these are only like 1 day, 2 days, 3, 4 days, but by the time you get here, 10 days have gone by, so we want to know what that answer is. Now, you can keep multiplying to get there if you want to, but I'm going to show you guys another way to do it. All right, so on the first day, what I want to demonstrate with you guys is what exponential functions are with this particular problem here. This is an exponential function. So here's a nice definition of an exponential function for you. An exponential function is one that changes by multiplication. Okay, so from 1 to 2 is a multiplication factor, 2 to 4, and they're all being multiplied by the same amount, right? So we start off with 1 person on the first day, but to get to the next row, what we have to do is we have to, let me write this a little bit different. To get from here to here, we take that last day there, right, we multiply it by 2, correct? And then we do that again. So we take that first person, double him, and then double that again, right? And then to get from here to here, we take what we had and we double it again, right? And every time you're multiplying by 2. So what's a better way, though, to write this expression rather than just putting 1 times 2 times 2 times 2? How about 1 times 2 to the power of 4? Okay, so since this thing is increasing by multiplication every time, multiplying the same thing repeatedly, you get an exponent, okay? This is an exponential function. What did that number represent? Well, that number in the front represented our starting amount, right? This represented what we were multiplying by repeatedly, right? And what this number represents is how many times we multiplied, right? So the first number represents how many people we had at the beginning, 1 person. And we multiplied by 2 that many times, right, to get to this particular spot here. So if I wanted to find this one down here, instead of multiplying by 2 that many times, I could write this, right? I could say I'm starting with 1 person, And to get to the 10th day, I need to multiply by 2 10 times. Okay? And that's where, we're going to probably be using calculators a lot today for this, but if you did this, you would get 1,024. Okay? So that's what an exponential function is. Just basically, it's a set of data that increases or decreases by multiplying some common factor all the way through. And that's why you get an exponent out of it. Mm-hmm.
Why isn't it 32?
Because look at the difference here. We're not going from 4 days to the 5th day, right? We're going from the 4th day to the 10th day. So I skipped numbers. So if you wanted to complete the table, like on day 5, it would be 32. Day 6 would be 64. 7 would be 128. By the time you got to the 10th, it would be 1,020. Okay, we good? Let's jump forward to the next part now. So what is an exponential function? An exponential function is a function that changes by repeated multiplication of a growth factor. So that number that you're multiplying by repeatedly, that's called a growth factor. So you might want to label these. We're going to be using that vocabulary today. That's called a growth factor, okay? For today, the number in the front, we're just going to call that the starting amount. We're going to call this our input. That's the number we're going to plug in, and the answer that we get after doing that, that's our output, right? So, so one of our objectives today was you guys should be able to tell me what an exponential function is. Well, an exponential function is one that changes by repeated multiplication, right? But how can you tell when you're looking at an exponential equation, okay? Like for instance, this is not an exponential equation. Okay? But this is. Oh, no it isn't. Sorry. So how can you tell when you're looking at an exponential function? It's whenever the input variable is a power. Okay, so if your x is in the power spot, that's what makes it an exponential function. Okay? So that's how you can tell when you're looking at an exponential function. And that's what Chapter 8 is all about. Doing all the regular stuff that we usually do with them, but we're going to kind of explore these things a little bit more. So you've invested money into a bank account, let's say. The bank promises to give you 50% interest every year. Okay, what that means is they take, now no bank would ever do this, by the way, they'd go broke, but just to make the problem easier, what that means is at the end of the year they look at what's in your account and they take 50% of that and they add it on. Okay, that's what interest is. Complete this table below. So let's say that you invested a whopping $16 into your account, right? 1 year has gone by. Does anybody know what the next number is going to be? It'll be 24. Why? Well, because remember they're giving you 50% of what you had. So I had 16, correct? So if you take half of 16, which is 8, and add that on, you get to 24. Okay? Why don't you guys try the next one here? Try to fill out the next few blocks here and see if you guys can get those. You're going to take half of the number and then add it on. So let's do one more together and I'll let you guys do the rest. So what would the next number be? You guys see why it would be 36? Because half of 24 is 12. Add that on to 36. All right. You guys try the rest. Pause for a second. Okay, so let's go ahead and finish this up here. So next number would be 54. because half of 36 is 18. Add that on, and you get 54. Half of 54 is 27. If we add that on, what do we get? And then the last one, 121.5. Okay, thank you. Okay, now this one doesn't seem to be exponential based on what I told you guys earlier, but it is, and I'll show you why in a second. Remember I said last time, exponential functions are functions that change by repeatedly multiplying a common factor over and over again. It's actually happening here, it's just not obvious. And let me kind of derive something here for you a little bit. So let's see. So let's start with this one. How do we get from 16 to 24? Well, what we did was we took 16, and what did we do to that 16? We divided it by 2, right? Well, why did we divide it by 2? And why is it half? What does it say in the problem? 50%. How do you find a percent of something? You multiply it by the decimal of that number, right? Don't you guys agree 50% means 0.5? Yeah. So if you multiply 16 by 0.5, what do you get? 8. Now after we get that, what did we do with the 8? After we took half of the 16, what did we do? We added it to that 16, right? Now I'm going to do some weird voodoo magic. You guys ready? So what do these two expressions have in common here? So they both have a 16, so I can factor that out. If I divide 16 by 16, what would I have? And if I divide this one by 16, all that's going to be left is that 0.5. And what is 1 plus 0.5? So really, in order to get from here to here, instead of doing all that crazy stuff, instead of taking half of 16 and then adding 16 to it, right? I could just take 16 and multiply it by 1.5. That's what we're multiplying by every time. Okay? So, what would this problem be? What was my, if I wanted to write this in this form here, in exponential form, what would my what would A be? That's my starting amount, right? And what's my growth factor? What am I multiplying by repeatedly? 1.5. And there's that exponential function. Okay? So this is kind of, there's a sneaky number in here that kind of just makes an appearance. We understand where 16 comes from. That's the starting amount. We understand where 0.5 comes from. That's the decimal version of that percentage. But that 1's a weird number. It just kind of pops in. But it's because we're adding the decimal to the original. And when you factor it out, you get a 1. So that's why that 1 sneaks in there. Okay? All right. I think I skipped a slide. All right, let's do this one here. Suppose that you drink 16 ounces of coffee, and as your body metabolizes the coffee, it manages to eliminate 50% of that caffeine in your body every hour. So metabolizing means your body's digesting it or using it somehow. Hey man, good morning. Okay, well, welcome. Happy New Year to you. You're welcome anytime. Feel free to sit where you like, bud. So your body's using up this caffeine. I've tried to pick some nice simple numbers because I'm not really trying to get you guys to master the basic procedure, the math right now. I just want to get the concept. So does anybody know what the next number would be? Let's see why it's 8. 8? Okay, suppose that you drink 16 ounces of coffee and every hour it uses 50% of it. So what's 50% of 16? It's 8. Now that's not why this number's 8 though. I mean, it is and it isn't. It's kind of, this might not have been the best number to pick. But let's do the next one. What's the next one? 4. 0. No. Lost me there, sorry. What would be at the 4th hour? There you go. All right, we're cutting it in half every time, right? What's the next one going to be? You really wanted to go to 0, don't you? It's not 0, though. It's 0.5. How many times would you have to divide before you get to 0? You would never. So here's the idea. In the real world, right? Eventually, your body gets rid of that caffeine. But mathematically, you could divide a number in half forever and never get to zero. You get smaller and smaller and smaller, but you'll never get there. Okay. So we're going to talk about that a little bit as the days progress on. That these functions have what's called an asymptote. They get closer and closer to a number, but they never get there. So this one would have an asymptote at zero. It can't get there. It will never equal zero. All right, so there it is. Now, in this one, we can kind of approach it the same way. Now, I know you guys. I think it's because of the number I picked. I made it 50%, so it made it a little bit easier. What were we multiplying by every time? 0.5. 50%, right? So 16 times 0.5 gives you 8. And 8 times 0.5 gives you 4, etc. Right? So we're multiplying by 0.5. But I want to show you guys something a little bit different. I'm going to make it harder than it is originally, but it's for a good reason. So your body's losing 50% of the caffeine every hour, right? So how do you find 50% of something again? You multiply it by 0.5, right? How much was originally in your body to begin with, though? 16, right? So this is how much your body is losing, right? And this is how much you had. So if you had this much and you lost this much, you would be left with 8. And you would get there by doing what here? You would subtract it. You take what your body had originally and subtract from it 50% because you're losing 50%. Okay? Now, why am I showing you that way instead of just doing what's obvious over here? Because I want to show you guys something. What do these have in common? But what's different this time? We're minusing because we're losing, correct? So instead of 1 plus 0.5, it's 1 minus 0.5, which is 0.5. So you guys see how this big ugly thing Mr. Bailey made look harder than it needs to be, and this, which you guys kind of knew up front anyway, just multiplying by half. They're really the same, and that's because 0.5 is exactly half. It wouldn't do that with another number. So, so knowing all that good stuff, then let's proceed. Sorry, I'll pause for you. All right, so let's continue. So I showed you guys an exponential function a little while ago, right? It was this thing. But I'm going to write it a little bit differently this time, okay? This piece here and this piece here are the same. I'm just writing them differently. Instead of just putting a b there, I'm putting this because I want to show you guys how you get that number sometimes. That b is not always obvious in a word problem. Remember how we had that 1 plus or minus something, right? So this piece is what we call the growth factor. We already talked about that, right? The b is the growth factor. So this whole thing here is the b. So that's your growth factor. 1 plus or minus r is your growth factor. But some more specific details is this number here, that decimal that we're adding in or subtracting out, that decimal, which comes from the percentage, that's what we call the growth rate. So we have two vocabulary words here. The R is the percentage that they give you in decimal form, okay? But when you add or subtract it from the 1, that's when you get your growth factor. That's what you're actually multiplying by repeatedly. Something else to take note of is the plus and the minus. Plus is whenever your function is growing. Minus is whenever it's decaying, is what we call it. It's getting smaller, okay? So like in the example of the coffee, it was decaying, it was going away. Whereas in the other one, what was it? It was the bank account giving you money, your amount was growing. So when it's growing, you're going to add the percent rate, the growth rate that they give you. When it's decaying, you're going to subtract the growth rate that they give you, okay? And then after you add or subtract that growth rate from 1, that gives you one number that we call the growth factor. And that's the number that you're actually multiplying by repeatedly, which makes it an exponential function. All right, guys. So let's take a look at the actual types of problems. That was all just kind of like front-loading stuff to kind of get your minds ready for the concept. You know, we know what an exponential function is now. It's something that increases or decreases by multiplying something repeatedly, and that something's called the growth factor. And you get the growth factor by subtracting or adding the growth rate to the value of 1. And we also know what the general formula is now for an exponential function. It looks like this, where A is the starting amount, R is the growth rate, plus is for growth, minus is for decay, and after we put those together, the result is what we call the growth factor. All right, so let's go ahead and take a look at this. The concentration of C14 atoms in a 200, hello. The concentration of C14 atoms in 200 milligrams of an organic specimen decays at a rate of 11.4% every 1,000 years. Write a function for the concentration of C14 atoms of a 200 milligram sample after T 1,000 years. So that's, gosh, that's a lot of words there. But first of all, I want to describe the story to you. This is kind of how people date things. There's a radioactive isotope of carbon within organic material. And so, you know, if you dig up a specimen of some kind as an archaeologist, right, you know, well, this thing probably had about this much carbon-14 to begin with, but now it only has this much. And we know it takes this long for half of the carbon to go away. And they can calculate or estimate the age of an artifact in that way, right? So what they've done is they've found something. They're not telling us what it is, but 200 milligrams. That's what they're holding on to. It has 200 milligrams of this C14. And here's what they know scientifically. They know that 11.4% of that goes away every 1,000 years. So whatever's there, 11.4% of that decays away every 1,000 years. Okay? So this is an exponential function. You can kind of tell this is a percent there, but that's not fail-safe. But when you see a percentage there, it's telling you that you lose 11.4% every so often. That's exponential. You lose that much or you gain that much every so often. That's exponential. So we know it's going to look like this. Okay? All right, so we said A represents the starting amount, right? So what's the starting amount? Is this growing or decaying? And R is the growth rate or the decay rate. And it's the decimal form of the percent. So what's the decimal form of this percent here? It's 0.114. So here's how you do it if you guys don't know. 11.4%. You take the decimal, you move it to the left twice, and that gives you the decimal form of the number. Okay, so it's 0.114. Yes, it does. So so that's a good question. I'm glad you're pointing that out. So the X here represents thousands of years. So if you plug in 1 for X, that means 1,000 years have gone by. Okay, if you plug in 2, then that means 2,000 years, etc. Okay. Okay. Someone with a calculator, help me out, please. What is 1 minus 0.114? Okay. Cool. I kind of got ahead of myself there and I wasn't even answering the question. So let's do that. What was the starting amount? 200. What was the growth rate? Yeah, you could write it as a percent, or this. I would do both just for now while you're learning it. Write an exponential function to model this. I just did that up here. So here's my exponential function. It's 200 times 0.886 x equals y. Now what's the growth factor here? Yep. The growth factor is this number, the number that you get after you add or subtract the 1. That's your growth factor. And now we get to do our calculator work. It says, how much will there be after 5,000 years? So x in this problem represents 1,000 years, and y in this problem represents how much is left. Okay? So we're basically taking the original amount and we're finding 88.6% of that every 1,000 years. And the output will be how much is left. So let's go ahead and do this. Different calculators may work differently, but if you're using any of mine, they'll all be the same. So we want to find 5,000 years, so I'm going to plug in 5 for x, because x represents 1,000 years. Okay? Okay. So the blue ones, and maybe you grabbed your graphing calculator, they do the same thing. If you're using your cell phones, it might be a little bit different. When you're using when you have these kinds that can type a whole number sentence in there before you push equals, then you can do what I'm doing. But if you're using a cell phone where you have to do one operation at a time, you need to follow your order of operations. Like in this, if you wanted to solve this, what would you have to do first? You would have to do the exponent first. You'll probably be tempted to multiply first, but don't do that. You would do the exponent first. But if you're using one of these calculators that can actually hold math typing expressions in there, then you can just type it in exactly as it looks. But here's how you're going to type it. You might want to write this down, because I found last year students had trouble with this. You're going to push 200, parentheses, 0.886, parentheses. Then you're going to find that button, and then you're going to type 5, and you don't have to use parentheses on the 5, but later on we're going to find that that's helpful. So I'm just going to get you in the habit of it now, but for now you don't technically need parentheses on the 5. So 200 parentheses 0.886 parentheses. Here's that little arrow button I was telling you about, and then parentheses 5 equals. So that's how much would be left after 5,000 years. It started at 200 and it goes down to 109 right now. Okay. $109.194. Let's round it to the third decimal place. I think I changed my slide. I don't have the right word problem back there anymore. Can I erase? Some pencils moving. Sure.
Did we just assume that there was a 1, or it's part of the equation?
It's part of the formula. Yeah. I like that. I kind of like the way that she just said that. So the decimal thing might confuse some people, but so we're talking about how you move it twice to the left. Well, I like how she said it. You basically just divide it by 100. So if you take 11.4 and divide by 100, you'll get 0.114. And I think the one that really gets people is this. Like if I told you we had 5%, a lot of times I get people putting that as 0.5. but that's not 0.5. It would be 0.05. Because if you take your decimal and move it twice, you have to throw a 0. So you got to be careful with those single-digit numbers. They throw people sometimes. All right, let's proceed. I'm going to do one more. I think I have one more example, and then we're going to just practice it a little bit. So there's 20 bacterial cells in a petri dish, and they increase by 5% every hour. What's the starting amount? 20. What's the growth rate? 5%, or 0.05, right? Let's write an exponential function to model this scenario. All right, so that's my work up here. Oh. All right, starting amount was 20. Growing or decreasing? R is? So my equation will be 20 times 1.05x to the x power equals y. So what's my growth factor? That's right. So in this problem, you guys, what do you think x represents? Yep, those represent your hours. What does y represent? Well, that's true, but in the word problem, it represents the number of bacteria that we have after that many hours have gone by. That says number of bacteria. Can't read it. All right, so number 5 says, how many bacteria will there be after 1 day? Careful with that one. So we have 20 times 1.05 to what power? 24. Why is it 24? Because 1 day equals 24 hours, and we're dealing in hours, right? So if they say a day, you're going to have to convert that. And then we get to use our calculators. So don't forget how to type it in your calculator. It's 20 parentheses 1.05 caret symbol 24. And you should get your answer. So we have 20 should get 64, and since we're talking about a certain number of cells, can't really have half of a cell, so probably just round it to the nearest whole number. You could round down too, technically that's an argument, because you haven't gotten to 65 yet, but you're closer to 65 than you are 64. All right, so I'm going to throw some student practices at you guys. Is anybody still writing this? No? All right, so I'll let you guys try a couple of these for a minute. Okay, so the growth rates. Amanda, what did you get for your growth rate? 0.035. I want to make sure you didn't put 0.35. It's 0.035. You divide this number by 100. Oh, there you go. You join us? Yeah. Welcome back. Long time no see. All right. Next we have write an exponential function. So What'd you get for that, Braden?
You want it like one added to
Sure.
you got 5,000 in parentheses 1.035.
There you go. Good. And what's our growth factor? Anybody? 1.035. What will the population be after 10 years? It should have been like 7,053? 52? If you round up, maybe. You can round down, that's reasonable. Or you can round up. Either one is good when you're talking about distinct, like a discrete number like that. Let's see. Next one, I'm going to buzz through. I don't want to run out of time here. I'll put it up if you're interested, or you guys can go. But see you guys tomorrow.
No.